Okay, so hi everyone. So welcome back to this new video. So today in this video we will be discussing this problem from Codeforces Educational 180 Round Div 2, and the name of the problem is Reachability and Tree, and it was the fourth problem, and this problem is rated 1700, right? So let us start reading the problem now. So the problem reads like this, that let u and v be two distinct vertices in a directed graph. Let's call this ordered pair u comma v good if there exists a path from this vertex u to this vertex b along some edges of the graph. So you are given an undirected tree initially consisting of n vertices and n minus 1 edges. So the usual description of a tree. Then we have to determine whether it is possible to assign a direction to each of the undirected edge of this tree such that the total number of good pairs is exactly n. So if it is possible, we have to print any way to direct the edges resulting in exactly n good pairs. So here we are given an example. As you can see that initially this is a tree consisting of 5 nodes and 4 edges. For this tree we have to direct all these undirected edges in such a way that at the end we will get a total of exactly n good pairs. So the description of good pair is written here. So we call a pair u comma v good if there exists a path from vertex u to vertex b along some edges of the graph, right? So if we consider the edge here from 3 to 1, so it is possible to go from this third node to this first node via this edge, right? So that's why we will say that this pair, that is 3 comma 1, is a good pair. Similarly, if we consider this pair, that is 3 comma 5, then it will also be a good pair because it is possible to go from this third node to this fifth node via some edges, which is only this edge in our case, right? This edge. So that's why we can say from this observation that every individual edge, no matter in what direction it is directed, it will always be called as a good pair because it will always be possible to travel between any two adjacent pairs, right? So this is one critical observation. So let us now read this question further. So in the input, first we have to take the number of test cases that can go up till 10,000, and then the first line of each test case contains one integer n that can go up till 2 into 10 to the power 5. So this n is the number of vertices in the original tree, and then it contains the next n minus 1 lines describing the edges of the tree, which will consist of two integers each, that is ui and vi, connected by this ith edge. So it has to be undirected initially. So it is guaranteed that the edges in each test case form an undirected tree, and that the sum of n over all test case does not exceed 2 into 10 to the power 5. So in the output for each test case we have to print a no if it is impossible to direct all the edges of this tree and obtain exactly n good pairs of vertices. And if it is possible to do so such that we get a total of exactly n good pairs of these vertices in the whole tree, that is a directed tree, then we have to print yes, and then we also have to print these n minus 1 pairs of integers, that is the orientation of each of the edge, that is the edges directed from ui to vi. And if multiple answers are possible, we can output any, and also we can print the edges in any order. So this is the whole problem here. So let us try to understand this problem even in more depth by taking these examples one by one, right? So let us now go to the blackboard. So this is the very first example given in the question. So as you can see that in this example there are a total of 5 nodes, that is the value of n is 5, and thereby we have 4 edges. So this is the first edge, this is our second edge, this is the third edge, and this is the fourth edge, right? So our task is to direct all of these undirected edges in some direction, right, in such a way that we will get exactly a total of n good pairs. So if I direct these edges, let's say I direct this edge present between third and 5 node in this direction, and also I direct the edge present between this 3 and 1 in this direction, and also the edge present between 1 and 2 in this direction, and finally the edge present between 4 and 2 in this direction, right? So what has happened after I directed the edges in this direction? So if you now calculate the total number of good pairs, so if you remember what was the definition of good pairs, so we call a pair u comma v as a good if we can simply go from this vertex u till this vertex v via some path, right? And as I told you before also, that any two adjacent nodes directed by a edge will always be a good pair. So here we can say that this 3 comma 5 is a good pair, this 3 comma 1 is a good pair, this 1 comma 2 is a good pair, and this 4 comma 2 is a good pair after we have directed in such a way, right? So that's why we have 4 good pairs as of now, right? So we have a total of 4 good pairs already. And since it is mandatory to direct all of the undirected edges in the tree, so that's why we can also draw one conclusion from this, that no matter what tree is given, if we direct all the undirected edges in any order, like in any direction, then we will always get at least a total of n minus 1 good pairs. Why? Because there are a total of n minus 1 edges initially, right? So since there are 5 nodes here, so that's why we have 4 edges here. So this is the first, this is the second, this is the third, this is the fourth, and that's why for every pair of an edge we will always get one good pair, right? So that's why the total number of good pairs we will have, at least in any example, will always be n minus 1. But our task was to get a total of n good pairs, right? And not n minus 1. Since our task was to get a total of n good pairs, and we already have a total of n minus 1 good pairs in any example, right? So our only task now is to get just one more good pair. So if we are able to get this one more good pair, then the total number of good pairs we will have will be n, right? And this is what we want. So we just want one more good pair in our example. So I hope you understood this thing. Tell me, in this example, if I have directed the edges in this manner, then how many total good pairs we have? So earlier I told you that we total have 4 good pairs already, that is this 3 comma 5, then this 3 comma 1, then this 1 comma 2, and then this 4 comma 2. But are there any more good pairs? If you see carefully, then what was the definition of a good pair? So the definition of a good pair was very simple, that a pair of u comma v will be called good if we can go from a vertex u to this vertex v via some path, right? So suppose if we start from this third node and we go via this path through this one node in order to reach this 2 node, right? Then we can definitely say that this pair of 3 comma 2 is a good pair, right? Why? Because we are able to go from this third node to this second node via this path. So this is a simple path consisting of 2 edges, and that's why this 3 comma 2 is also a good pair. So the total number of good pairs that we have now is, this is the first good pair. If you go in this path, this is the second good pair, this is the third good pair, this is the fourth good pair, and finally if we go from this 3 to 2 via this path, then we can say that this 3 comma 2 is the fifth good pair. So the total number of good pairs we are getting in this example is 5, and you can check that there are no other good pairs other than these 5. That's why, since we wanted a total number of good pairs to be exactly n, which is true in this case, so that's why we have to print yes here. And after printing yes, we also have to print the direction for each of the edges here. So since this 3 is directed towards 5, so I will say 3 space 5. Similarly 3 space 1, 1 space 2, and then this 4 is space 2. So this is the thing that we have to print for each example. So I hope you got this concept till now. It is not that much hard to understand. So the question is, now how will you approach this problem, and what logic will you apply? And how will you know that if it is possible to get exactly total of n good pairs or not? So this is the second example of the test case. So in this test case, the total number of nodes present is 5, that is from 1 to 5, and thereby we have given 4 edges also, right? So our task is to direct all of these edges in such a way that the total number of good pairs here will be exactly n, that is n should be equal to 5. So let us start directing the edges now. So if I direct the edge present between 1 and 2 from 2 to 1, that is like this. And then if I direct the edge present between 3 and 1 from 3 towards 1. Also if I direct the edge present between 1 and 4 from 4 towards 1 like this. And at last if I direct the edge present between 4 and 5 from 5 towards 4 like this. So if we do this, then can you count the number of good pairs? No matter what we do, we will always be having a total of n-1 good pairs at least, right? So we already have n-1 good pairs, which are as like 3, 1 and then 4, 1, then 2, 1 and then this 5, 4. So these 4 are already good pairs because we can go from this node to this node, or from this node to this node, or from this node to this node, or from this node to this node. So that's why we already have n-1 good pairs and we want just one more good pair. So if we want one more good pair, then suppose if I start moving from 4 in order to reach 1 via this path, then I can simply use this path through this 4th node in order to go from 5 to 1. And since I am able to reach from this 5th node to this 1 node via this path, so that's why I can say that this 5, 1 is another good pair. So that's why the total number of good pairs that we will have now is this. So it will result into a total of n good pairs, which we wanted ultimately. So that's why this is a valid orientation, and that's why we will print what? So we will print a yes, and then we will also print a direction for each of the edge. And since we can print it in any order, so that's why suppose I print 2, 1, then 3, 1, then 4, 1, then 5, 4. So this is a valid output. So I hope you got this. Now let us move to the third example. So this is the third example given in the test case, and it is quite small. So as you can see that the total number of nodes present in this is exactly 2, right? Thereby the total of n-1 edges are present, which is this edge only, that is one edge, that is 2 minus 1. The number of total good pairs that we want now is what? We want it to be exactly equal to n, right? That is 2. And since we know that the number of edges given initially, which is n-1, will be the at least number of good pairs we already have in the graph. So that's why we already have a total of 2 minus 1 good pairs, that is one good pair. And if you look carefully, then what it is actually, so if I direct this edge in any direction, let's say I direct it from 2 towards 1 like this. So if I direct it in this way, then I can say that the pair 2, 1 is a good pair, right? Or if I direct this in this direction, then I can say that this pair 1, 2 is a good pair. So that's why you can direct this edge in any one direction, and if you direct it, then you will get exactly of one good pair, either 1, 2 or this 2, 1, right? That's why the total number of good pairs we can get from this graph is just 1. So this. And since we wanted the total number of good pairs to be exactly 2, because the value of n was 2, so the total number of good pairs we wanted was 2. But what are we getting actually? We are not getting 2. Instead what we are getting is just one good pair, either 2, 1 or 1, 2. So that's why we can say for this particular graph or this particular tree, we cannot direct all the undirected edges in such a way that the total number of good pairs we will get will be equal to n. So that's why for this, what we will print? We will just print a no and nothing else. So now let us move to the last example of the test case, that is the fourth example. So this is the fourth example given in the question, and as you can see that here the total number of nodes present here is 4, and thereby we are given 3 edges here like this, which are undirected initially. So we have to direct it now in order to get exactly of n good pairs. So since the value of n here is 4, so that's why the total number of good pairs we want is 4. And we know that the total number of good pairs we already have is 3 at least, right? So we already have a total number of 3 good pairs, and we just want one more in order to get it exactly equal to n, that is 4. So let's start orienting the edges now. So let's say if I orient the edge present between 1 and 3 from 3 towards 1 like this, and then if I orient the edge present between 1 and 2 from 1 towards 2 like this, and finally if I orient the edge present between 2 and 4 from 4 towards 2 like this. So now if you start counting the total number of good pairs, then you can write it as that 3, 1 is a good pair, this 1, 2 is a good pair, and then this 4, 2 is a good pair. So these are 3 good pairs of path length equal to 1, right? And also there is one more good pair. If we start moving from this third node via this path through the one node in order to reach the second node, then we can say that this 3, 2 is also a good pair, because we can go from this third node to the second node via this path. So that's why I can say that this is giving us another good pair. So one more good pair of path length 2 this time. So 2. So since we are able to get a total of 4 good pairs, so if you look carefully, are there any other good pairs other than these 4? So let's check one by one. So if you try to move from this first node to any other node except 2, then you simply cannot go. Similarly, if you try to go from this 2 to any other node, then it is not possible. So that's why 2 will not create a good pair with any other node that is originating from itself. If you try to go from 4 to any other node, then it will not be possible to go to any other node except this 2. And finally, if you start moving from this 3, then you can get exactly of 2 good pairs. First from this 3 to 1 via this path of length 1, and also you can move from this 3 to 2 via this path of path length 2. So another good pair 3, 2. So these 4 are the only good pairs that you can get in this example, and since this is equal to the total number of nodes, which is 4, so that's why what we will print, we will just print a yes. And after printing this yes on a new line, we also have to direct the edges, that is we have to print the edges. So that's why we will print something like 3, 1, 1, 2, and then this 4, 2. So that's why this is a valid output for this example. So I hope you understood these 4 examples in very detail. It was not that much hard to understand each one of them, because the concept here is quite simple only. So let's consider this following example that I have considered by myself. Our task is to direct all of the given undirected edges in one direction, right? And we have to orient it in such a way that we will get a total of exactly n good pairs. So since the value of n here is 6, so we want a total of 6 good pairs. And we know that no matter in what direction we will orient all the undirected edges, we will get a total of 5 good pairs already, right? So we just want one more, not even 2 or 3, we just want one more. From common sense, you can tell, or anybody can tell, that if we want one more good pair, then the path that extra good pair will take will simply be of length 2 and will consist of 3 nodes. And that's why we can say that this A, C will be an extra good pair that we need, right? And nothing more. So if we try to do the same thing here, then let's see if it is possible here or not. So our requirement is very clear now, that since we just need a path length of 2 consisting of 3 nodes in order to make these extreme nodes as a good pair. That's all we want, right? If we consider any 3 such nodes, so we can consider it like here 1, 4 and 5, or you can take 1, 4 or 2, or you can take this 6, 5 and 4, or you can take this 3, 5 and 6. So all of these things you can take. You can even take this 2, 4, 5, or this 3, 4 and 5, right? So suppose I take this one, that is 1, 4 and 5, in order to create that extra good pair. So in order to do that, let's say I direct this edge from 1 towards 4 like this. And then since I have considered this portion in order to create that extra good pair, so it means that I have to direct this edge in this direction only. Because if I do it only in this fashion, then only I will get a total of one extra good pair between these two extreme nodes, that is 1, 5, and I will go through this path of path length 2 that we just discussed before also. So this is fixed now, we cannot change this. So this will contribute towards the extra one good pair that we need every time. And now we have to make sure that we don't get any other good pairs of path length 2 or more. So since the edges remaining are this, this and this, so we have to make sure that no matter in what direction we align these edges, it should not it should never create a path length of 2, right? So let's try out all the possibilities, right? So I'm just trying out all the possibilities now. If we direct this edge, let's say in this direction, then what will happen? See carefully. So I can now go from this first node to this 4 node, and from this 4 node I can go to this 2 node. So this is generating one more good pair that we don't need now. So it means that directing it in this direction is simply not feasible. So we will not direct it in this direction. So let's try the opposite one, because it is the only remaining possibility. We cannot left it undirected, right? So if we direct it in this way, then again this is problematic, because we will go from this 2 to this 4, and from this 4 we will go to 5. So this is again contributing one more good pair, that is 2, 5 via this path. So it means that no matter in what direction we align this edge, we will always get one more good pair. And the same thing will be true for this other part as well. So no matter what path you pick of path length 2, either it is this one or any other, right? So let me take another path in order to show you that what I'm saying is absolutely true. So suppose instead of this path I'm taking this path now. So this will give us an extra good pair of 1, 2 that we need, right? So this is we need. So we don't need any other good pair of path length 2. So if I try to orient these edges now, so it is obvious that I cannot direct this edge in this direction, because if I do it, then it will create another good pair, because we can go from 5 to 2, then it will give 5, 2, which we don't want. So we will not align it in this direction. Let's align it in this direction now. But even if we align it in this direction, then it will create 1, 5 as the good pair, because then we can go from 1 to 5, right? So it again means that we cannot align this edge in any of the direction. And if you take any 3 such consecutive nodes, then you will realize that you will never be able to get just exactly one more good pair. You will always get 2 or more. So that's why we have to print no in that case. Now let's take another example where it will be possible to direct all the edges and get exactly n good pairs. And then we will see the difference between that example and this example, that what exactly is that thing that is preventing us to get exactly one more good pair. So this is the new example that I have considered myself. So if you remember, then what we want a total of n good pairs. So here the value of n is 7. So we want a total of 7 good pairs. And we know that we already have 7 minus 1 good pairs, that is we already have 6 good pairs now, right? So we already have a total of 6 good pairs. And we just want a total of one more good pair, right? So we want one more good pair in order to make it equal to 7, right? So let us now try to derive this one more extra good pair, and we just want one, so keep that in mind. And by now we know that in order to create this extra good pair, we need a path length of exactly 2, because even if you take a path length of more than 2, like 3, suppose you take this, then along with getting 1, 5 as a good pair, you will get 1, 6 as the good pair, or 4, 6 as the good pair if you align it in this direction and take this. So that's why it is very important to take a path only consisting of 3 nodes and 2 path lengths, such that you will only get a total of one more extra good pair between these extreme vertices, right? So if we have to take such a path length of 2 from this graph, then let's say we can take either this, or we can take either this, or we can take either the center one like this, or we can take either this, or we can take either this finally. So if we have decided to take this path, then we have to orient the edges in this way in order to create this 1, 5 as the extra required good pair here, right? So this 1, 5 is the extra required good pair. And after doing this, we have to make sure that we will not generate any more good pair. Now let us try to assign a direction to this edge. So either we can assign it like this, or we can assign it like this. So if we assign it like this, then it will be a problem, because after assigning it in this direction, we can go from 1 to 4, and then we can go from 4 to 2. So this will create another good pair of 1, 2, along with creating this 1, 5, right? So we want this but not this. So that's why doing it in this direction is not feasible. And even aligning it in this direction is not feasible, because then we will go from 2 to 5, and this will create another 2,5 as a good pair, which we don't want. So it means that we can neither align it in this direction nor this direction. And since it is mandatory to align all the undirected edges in some direction, so that's why I can say that choosing these three vertices in order to create this extra good pair is not feasible. So we will not choose these three. If we take this path, the extra pair that will be created will be 1, 2 here, which we want, and we don't want any other. So if we have to assign a direction now to this edge, then if we assign it in this direction, then it will create 1, 5 as a good pair, which we don't want because we already have 1, 2. So we will not assign it in this direction. But if we assign it even in this direction, then it will create 5, 2 as the good pair, because we can go from 5 to 2 then. So you can neither align it in this direction nor this direction. So that's why choosing these three consecutive vertices is again a problem. So we will not choose this. So if you have noticed, then what we have done till now is, whenever we were choosing these three consecutive vertices in order to create that extra one good pair, we were always choosing all these three vertices such that the middle vertex never had a degree of 2. So let me show you the same thing in the first example, how the degree is getting importance in this question. Let us now calculate the degree for all the vertices. So the degree of 4 is 1, the degree of 2 is 2, the degree of 1 is 2, the degree of 3 is 2, and the degree of 5 is 1. So that's why, since in the whole graph there is some vertex for which the degree is 2, you can imagine it as something like 2 edges will be connected to that node. So that's why the degree is 2. So if this condition is possible, then we can say that a simple path can be generated via this 2-degree node, right? And if we are able to do this, then in the remaining part, we can always orient the remaining edges in such a way that it will never create a simple path. Let's see the same thing in the second example. So here this was the simple path length of 2, if you remember, right? So here if we write the degree, so the degree of 1 is 3, the degree of 2 is 1, the degree of 3 is 1, the degree of 4 is 2, and the degree of 5 is 1. So here also there is at least one node which has a degree of 2, that is 2 edges are attached to it. So that's why we can consider that as a center node of a 3-node path, that is a path length of 2, and that will create an extra good pair that we need. And except this path, these two will be the remaining portions, right? So it will always be possible to align these remaining portions in such a way that they will never form a path length of 2. How? I will show you very soon. But since in this graph, as you can see, that is the third example, the degree of 2 is 1 and the degree of 1 is also 1. So there are no nodes which have a degree of 2. So since there are no nodes which have a degree of 2, so that's why we can say that we will never be able to generate a path length of 2. Because in order to create a path length of 2, we need a structure something like this, or at least 3 nodes. But since it will never be possible, so that's why the output is no. And then finally, if you look in the fourth example of the test case, then here, if you remember, then this was the simple path of length 2. So now for this fourth example, if I write a degree of all the nodes, so the degree of 3 is 1, the degree of 1 is 2, the degree of 2 is 2, and the degree of 4 is 1, right? So in the whole graph, there is at least one node which has a degree of 2. So whatever node has a degree of 2, that node can be considered as the center node for a 3-node path. So that's why if I am considering this path, then this node can act as a center node. Similarly, we can also have took this path as the valid path in which the second node would have been the center node, right? So if I do this here, it could have been something like this. So this 1, 4 would have formed the valid pair good pair instead of this 3, 2, right? And then we could have simply directed this 1, 3 in this direction. And after doing this, the good pairs that we would have would be 1, 3, 1, 2, 2, 4, and then this 1, 4, and not any other. So that's why this is also a valid example. So by now you must have understood one thing. We will always calculate the total degree of all the nodes, And after calculating the degree of all the nodes, if there is at least one node in the whole graph which has a total degree of 2, then it means that that node can act as the center node for the 2 length path, right? So here, if you calculate the degree, then for 1 it is 1, for 2 it is 3, for 2 it is 1, for 3 it is 1, for 5 it is 3, for 6 it is 1. So there are no nodes in this example which has a degree of 2. So that's why no node can act as the center node of that 2 length path, and that's why the answer is no. Similarly, if you look in this example and calculate the degree, then it is 1 for 1, 1 for 2, 1 for 3, 1 for 7, 3 for 6, 3 for 4 and 2 for 5. So there is at least one node here, which is fifth node in our case, which has a total degree of 2. So it means that this node can act as a center node for the 2 length path. We have to align it in this direction, right? So this thing is occupied now. Our only task remaining is to align these 4 edges, that is this region and this region, right? So once you're able to make sure this thing, it should be evident to you that in these 2 extreme regions of these 2 extreme nodes of this 2 length path, it will always be possible to direct the remaining edges in such a way that it will never create a path length of 2. And how will you do this? By turning the edges alternately. So suppose there would have been some extra nodes here, let's say like this. Just imagine it, because I want to show you. And also in this part of the graph like this, right? So if the graph were something like this and you needed to align the edges for this part now and this part now, right? Because everything is sorted till here. Then what you could have done is you could have aligned this 1,4 edge in this direction. Because if you align it in this direction, then this 1,5 will form a good pair which you don't want. Similarly, if we align this 6,7 edge in this direction, then it will be good to go. Because if you align it in this direction, then this 5,7 will form a good pair which we don't want. So what I am trying to do is, initially, whatever the nodes are connected to this extreme left node, we are directing the edge away from it, right? And for the right part, whatever the nodes are connected to this extreme node of this path length 2, we are directing the connected edge towards it. And once we do this, since we want to make sure that any path length is not of path length 2, so that's why now if we had to direct the edge from 1 to this node, then we will not direct in this direction. Instead, we will direct it in this direction. And we will do this in alternate fashion for all the nodes. It is away and then it is inward. It is outward and then it will be inward. And then again it will be outward. Similarly for this. And the same thing we can do in this region also. Once it is inward, then we can't do inward again, so outward and then inward. Similarly here, since it is inward, so we can't do inward, so outward for both. So that's why it should be very clear to you by now that if you are able to find a node of degree 2, then that node can act as the center node for that 2 length path which we want to generate an extra pair from it, from the extreme vertices. And in the remaining region, it will always be possible to orient the edges in such a way that a path length of 2 will never generate, because we will align the edges in alternate fashion. So this is the whole logic behind this problem, right? Now I think it will be very good for us if we move to the code editor and code this up quickly and see if we are correct in our logic or not. So let us now go to the code editor. So first we have to take the input for n nodes, and after this we have to take the input for the n-1 lines. Every line will consist of 2 integers u, v. So let's use an adjacency list of g in order to create this tree. So let us declare this adjacency list also here. And since I am using 1 based in the indexing, so n+1. Now, as I told you in the explanation, that we will be needing the total degree of all the nodes. So that's why what I will do here is, I will create another vector, let's say degree, which will hold the degree of all the nodes. And then here I will say that the degree of this u increased by 1 and the degree of this v also increased by 1. So in this way the degree for all the nodes will be calculated, and once this is done, we will check. So since this is degree, so let's name it as degree only. So once it is done, what I told you that we will check if there is any node which has a degree of 2. So that's why we will again iterate through this degree vector to check if the degree of any node is equal to 2. So if it is equal, then I can say that that node can act as the center node in our case, right? So that node will be considered as center node, and then we will break from the loop. Simple. So let me declare this variable here, and after this loop ends, if the value of center node remains equal to -1, then it means that there is no node that can act as a center node. So that's why we will print a no in this case, right? Like this, and simply return. So this is the case when it is not possible to direct all the edges in order to get exactly n good pairs. But if it is not the case, then it means that the situation is possible. So possible situation. And in that case, what we used to do, so as I told you that in that case, since this will be our center node, so in the adjacency list for this center node, only 2 elements will be present. One is this left one and other is this right one. So since we have to direct, so let's name it as A, B and C. So since we have to direct a edge from A to B and from B to C, so we will do the same thing here. So first we will print yes because it is a possible situation. And after printing yes, we will print these 2 edges of the path length 2. So that's why let's store it first. So I will say that this left extreme vertex is nothing but g of this center node in the 0th index position, and similarly this right extreme node or vertex rather is nothing but g of this center node in the first index, because it will only consist of these 2 elements. So we have to direct the edge from this left extreme vertex towards what? Towards the center node. And then on a new line, we have to direct the edge from this center node towards this right extreme vertex. We are simply printing these 2 edges, and now our task is to direct these 2 portions, and for that we will use a simple DFS in order to alternate the edges continuously. So to do this, I will simply call a DFS function first from the left extreme vertex and then from the right extreme vertex, and I will pass its parent as the center node. And why I am doing this? Because if I pass the parent of this 4 as 5, then it will never go from 4 towards 5. It will only go in this direction. Similarly, if I set the parent of this 6 as 5, then it will never go in this direction. It will only go towards the side that we want. So that's why I'm passing the parent as the center node. And we have to do it twice. First for the left extreme vertex and then for the right extreme vertex. So let us write the DFS function here. So first I have passed the node and then I have passed the parent, right? So how we traverse a tree? So we will just simply iterate through the childs like this. So we also have to parent the adjacency list, I guess. So let's do it. For auto C belonging to the childs of this node, if this child is not equal to this parent, it means that we can go in that direction. So I'll again call the DFS function starting from this child, and this time this node will act as the parent, and I will pass this G here. Since we have to orient the edges in alternate fashion, that is first when we have started our DFS call, then we have to orient it outwards, then inwards, then outwards, then inwards, and so on. So in order to do this, I will just use a simple flag statement. So let's keep it as 1. So if I pass 1 here and let's say it as flag, so I will check that if the flag value is even or odd. So if it is odd, then what it means? It means that I have to direct it away. So that's why I will direct it away, that is from the current node to this child. And if it is not the case, then it means that the flag value is what? The flag value is 0. Sorry, I think I should keep it as bool rather than ll. right? So this is a boolean value that I am passing. So if I have passed 1 that is true, so it means that I have to just check if this flag value is true or not. You can also check that using that even odd criteria, but this is more intuitive. So if the flag value is true, then it means that we have to direct it from the current node to the child. But if it is not the case, then it means that we have to direct it in opposite direction, that is from the child to this current node. And when the child DFS will be called, just invert this value of flag so that in the next turn the edge is oriented in opposite direction. So this is for the left extreme vertex. And since we saw that for this right part, we have to orient the edges first inwards and then outwards. So since we want the inwards first, that is from child to the node from where we are starting. So that's why I will pass a 0 here, because after passing 0, this will not be executed, only this will be executed. That is from child to node, which we want. So this, and here don't forget to pass the adjacency list, right? So once these two DFS functions are called, it will automatically print all the edges required, because it was told that we can print it in any order. So that's why we are printing it first for the left part, and then we are printing it second for the right part, and before that we have printed it for the center part, and just do a return. So I think I have written the complete code here. Let's now run it. So as you can see that we are getting the output. Obviously the order is not matching, but it is not an issue. So let's now try to submit it on the platform to see if we are correct or not. So as you can see that our solution is accepted. So this is the code that we just wrote, right? And I told you each and everything in very detail, what is the logic behind all this. So thank you so much for watching this video till now. If you really think you understood something new and found it interesting, please consider liking this video, because it is taking me a lot of efforts to create it daily. And also subscribe this channel if you have not yet subscribed, right? We are close to 500 subscribers. So please do it. And I have already created a lot of amazing content for the graph theory and the segment tree. So you can watch it if you have not yet watched, because I have also created a dedicated playlist for these two, right? So this is for the graph theory, in which a total of 12 videos are present as of now. And in this segment tree, a total of 9 videos are present. So yeah, please consider subscribing the channel. And if you have any suggestions for me, please feel free to write in the comment section. I will read it and try to act on it. So yeah, thank you so much for watching this video. Thank you.